Hello everyone, my name is Gaurav Arora. I'm a faculty of economics at IIIT Delhi, and let's get started with the first lecture of spatial statistics and spatial econometrics. So we will begin with some information about how this course will be conducted. So the primary objective of this course is to provide a graduate level maturity in statistical analysis for students of engineering, mathematics, statistics, earth sciences, economics, and other quantitative social sciences. So at the outset, we can see that this course will have wide applications. So, a wide range of students coming from different domains can take advantage from this course. I believe that statistical concepts are best understood with applications. So in this course, we will strive to have in-class exercises which will be applied in nature. We will have weekly assignments that will help students apply the concepts that are going to be learnt during lecture hours on real-world problems. And then there will be a lab component towards the end of this course, which will provide hands-on training on GIS software using ArcGIS, as well as some packages in R that have similar or even more advanced applications. So about the origins of spatial statistics. Spatial statistics is a relatively new science, perhaps the newest among the subdomains of statistics. There are several other subdomains of statistics. For example, there is biostatistics. Among these subdomains, spatial statistics seems to be the newest ones. The early applications of spatial statistics came from earth sciences, specifically in mining, where for coal ore estimation, that is the quality of coal available or any ore available inside the earth, is fundamentally not visible to the statistician, the miner, the analyst that is out there to dig that or extract that coal. So what we can achieve at best is that we can dig some holes at some locations on ground, and we have to predict what is the pattern of quality underneath the ground from what we can observe from few points on top of the earth where we have dug. Similarly, you have problems of oil exploration, so oil search campaigns done by petroleum industry have similar issues. Where should they send their next expedition, right? These are costly expeditions. So that's where statistics comes in. It tries to predict what would be the best optimal pathway in terms of extracting coal from ground or searching for oil. More modern applications are of image processing. Therein, we will look at satellite image data. That's one of the most popular applications of spatial statistics. There is medical imagery, MRI, fMRI. That is also where spatial statistics is finding its use today. In crop yield estimation for agricultural experiments, for insurance provision by business intelligence consulting firms, for conducting tiger census, by ecological and environmental scientists is also finding its use of spatial statistics. Finally, for regional planning, for example, planning bus routes in a city, planning a metro train network, where to put the next route, what should be the best, locations where, most residents of a city can find connectivity, will find applications of spatial statistics. So with that, let's define formally what is spatial statistics. So first of all, before we get to what is spatial statistics, we should understand what is statistics. Well, statistics is a science of uncertainty. So statistics posits the observations that we see around us in the world as fundamentally random in nature, right? But in this fundamentally stochastic or random real world around us, there is some order, and statistics as a discipline, as a science, strives to determine or identify order in disorder, right? So it takes a sequence of entities, a sequence of events. For example, climate change, right? If we want to understand the pattern of drought, so fundamentally statistics posits incidence of drought as a random event. What do we see is some observations of drought in the past, right? So let's say a drought happens in the Indo-Gangetic plains once in every 3 years. Sometimes it happens within 2 years, sometimes it happens after 5 in 5-year intervals, right? So statistics would take the sequence of events that have been observed in the past and then try to discover some kind of order in the sense of what is the average frequency, the median frequency or similar type of moments between two different droughts, and what kind of events precede this drought. Okay, so how can we predict the next drought? That's the basic basic line of inquiry. Spatial statistics adds a new dimension of where to this science of what and how in determining order in disorder. So it would then ask not only when will drought happen and how it will happen, how strong it will be in terms of its intensity, it will also ask where will it happen exactly in space. So we bring in a new dimension of space. If you want a little bit more intuition, you can think of the dimension of time. So time itself is a new dimension as far as time series statistics is concerned. In time series, you have a time origin t0, then you have t1 which comes after t0, then t2 that comes after t1, and so on and so forth. It keeps going till infinity, right? In space, you also have a point of origin, but then you can actually move in any direction from that point of origin as far that we can imagine. The four directions are north, south, west, east. That is something very natural that comes to us. So if we start to exploit these directions in space in doing statistics, that is what that's the toolkit that spatial statistics will bring to the table. Okay. So let's begin with some popular applications, all right? So, because we have to sort of combine concepts with applications in that spirit, let's see who cares about spatial statistics. So some of the most recent popular applications of spatial statistics have been, it has been a project by Facebook on expansion of internet coverage in Africa. Now, internet connectivity can be provided using different modes. It can be provided using landlines, using satellite signals, using drones, or even hot air balloons. However, which mode is best suited for which region depends on the demand for internet, which will come from the population density of that particular region. So if we are going to remote regions, let's say of Africa or even in India, where we do not really have a sense of population density, then what do? Well, then we can use satellites and data that comes from satellites to predict population density of a region which may not be otherwise known, and hence we cannot get internet to that particular population or that community at the best, in the most optimal manner. So Facebook employed satellite imagery and data science to predict population density for a large landmass of approximately the size of Africa. So it was a large scale application done using satellite imagery. And here is a particular data product that has come from this project of Facebook. Well, what you see is that on the northeast side of this picture or this map, what you see is a high resolution data that Facebook predicted using satellite imagery. And on the south, you have a low resolution data set that comes from administrative surveys. What you see is that in the bottom picture, you have a sense of population density, in the sense the lighter regions are low population density areas, the darker regions, the bright red regions are high population density areas. But in the bottom picture, a particular district can have a uniform level of population density, right? So if you have a white block or a white cell, it is saying that the population density is of certain level for this entire block, right? Whereas if you go to this north map, this map in the north, you can have difference in the level of population density in a block of similar size. Okay, so you can have lower density areas adjoining higher population density areas. So you have a higher resolution understanding of the region by itself. So this is powerful in the sense that it gives you a more sort of finer understanding of what's happening on the ground so that you can then allocate resources efficiently. Let's look at another example. So in another popular example of supply chain management, which is a more of a business intelligence domain example, satellite data were used to estimate the number of vehicles parked or density of parking area utilized for 100 Walmart stores across the United States. And then these were then correlated with those with the revenue streams and the sales of those stores. So what you see in this picture is that you are looking at a satellite imagery which has a parking lot. It has a parking lot, and some portion of that lot has cars in it, right? So you can first of all see through naked eye that some portion has cars, some portion has no cars, right? The other thing that you can see is that you can imagine that one can use software to actually count the number of vehicles that are parked in this parking lot. So you can tell at a given point of time how many vehicles are parked in this parking lot, which gives you a signal of how many customers, how many consumers might be visiting that Walmart store, this Walmart store at that given point of time. And that should then give you a signal of what should be the level of sales or level of earnings that this store may be experiencing. So satellite data can be used in such a way for business intelligence purposes. There are some other popular examples, and I have a hyperlink here. So if students are interested, if you are interested, please click on the hyperlink, go and read. There are more examples. For example, there is Amazon's famous inventory optimization problem that you'll find very interesting to read. Then there is prediction of crop yields for agricultural sector. This has become a very famous, very popular tool in the West, which has larger farms. For countries like India or low-income countries, prediction of crop yields is more challenging because we have smaller farms. So this is a problem, that is being explored by the research community at the moment. And then finally, as we have also remarked earlier, there is optimization of drilling search for oil discovery that is done in the petroleum industry. Recent, use of satellite imagery has been found in the Economic Survey of India 2021-2022. This is probably the first time a government entity is evaluating, development or tracking development, as they say, using satellite imagery and maps. So let's see what we find in the Economic Survey of India 2021-2022. So what you see here is nighttime luminosity on the map of India across space in 2012 and on the left, and 2021 on the right. So on the left, first of all, wherever you see a brighter light, that basically means that there is let's say, there is more incidence of lighting. It could be city lights, it could be residential lights, it could be street lights, whatever that is, all of that is aggregating, and if we click a picture from space, it looks like it tells us how light is spread at night time in these cities. So you see New Delhi. Of course, around New Delhi, you have a very large mass of light in 2012. So you have around Kolkata, and similarly around Mumbai, right? So these are metro cities. Of course, you will also see this around Bangalore, around Chennai. I'm only talking about these, right? So first of all, the spatial information is rich enough to tell you the density of the difference, the variation in density of night lights across different cities and different towns in India. If you come from a smaller town, maybe you can locate that in this map approximately and tell how much night light was there in 2012 at that time. On the right hand side, when we move to 2021, what is very clear is that the nighttime luminosity has on average increased in India, right? So if I were to look at a non-spatial statistic, I will have a nighttime luminosity index for 2012 and a nighttime luminosity index for 2021. And of course, 2021 index will be much higher than, maybe even double than 2012 measure, right? So that's one type of statistical analysis or statistical understanding of, data-driven understanding of nighttime luminosity in India. But you can do better. You can tell that the increase in nighttime luminosity has happened around the already existing cores in 2012. So luminosity has increased, but it has increased mainly around, New Delhi, Mumbai, and Kolkata, right? What has also happened is that the area that looks quite dark, which is the Bihar, Jharkhand, West Bengal, and let's say eastern UP, Uttar Pradesh, that is eastern Uttar Pradesh, which looks pretty dark around the 2012 period, seems quite bright. So this is where the increase, the net increase is going to be coming from a lot, right? So spatial statistics is powerful in the sense of not only telling us what has happened, how much it has happened, but it is also telling us where has it happened really, okay? So if I were to tell you, okay, the nightlight luminosity was x1 in 2012, it was x2 in 2021, and x2 was quite large as compared to x1. But then where has this increase come from? Well, it has come from the core of already existing high luminosity density around the metropolitan cities of India. But it is also coming from the heartlands, the not so developed regions that is Bihar, West Bengal, Jharkhand, and eastern Uttar Pradesh, right? So this is the interesting dimension that spatial analysis brings to the table. The next graph or the map that Economic Survey of India posits is the spread of commercial bank branches in India. So you can at the outset you can see the kind of applications that we are seeing as the first two examples in Economic Survey of India are very different. One is the nightlight luminosity, the other is bank branches. In this graph, in the left graph, we have the 2011 spread of commercial bank branches. Every dot by itself is a bank branch. Every dot on this map is a bank branch. So if you see higher density of dots, what you are basically saying is there is high density of bank branches in that area. So there is higher activity of economic transactions. The credit industry might be more dynamic in that region, right? So now from 2011, then we have a commercial bank branches spread in 2021. At the outset, what we are seeing is, well, there are definitely more bank branches in India from 2011 to 2021, right? And the number of bank branches, which is also coming from the economic survey, has gone up from 74,130 to 1,22,976. So there is indeed, a pretty high increase, about a 70% increase, if not double, about 80% increase maybe in the increase of bank branches. That's one way to understand the world around us, right? So how and how much, by how much and what. So what has happened? Well, the number of bank branches has gone up. By how much? Well, by about 70 to 80%, right? But where has it come from? Well, it is quite clearly coming from the region in Odisha and Chhattisgarh, where you do not see, you have this white map, a whitish map, which basically says there is less density of dots in this region, and which goes up quite drastically, at least in the coastal regions of Odisha, right? So this is another very good example. Then we have another example on net zone area in India. Here you can see again, you can have a statistic of what has happened. Net zone area has gone up. By how much you can calculate, but where has it gone up in the most? Well, you can see here that Jharkhand seems to have a quite drastic increase in net zone area relative to other states, right? You also see some of that in the southern states that I've marked here. So this is the type of extra information that spatial analysis is bringing to the table. Of course, if net zone area is going up, there is also a downside to it, that you can see shrinking of water resources. So here, we have an annual cycle of water storage at Stanley Reservoir in Tamil Nadu, and we are looking at 2016 to 17. So June of 2016 going up to May of 2017. So June of 2016 is just right about at the onset of monsoons. So we are looking at the size of the reservoir. It goes up as the monsoons play their role. The rains happen, and in October you have a larger size of water capacity in this reservoir, or water storage in this reservoir. And then just before the onset of monsoons, in May, you see that the reservoir actually shrinks, and the shrinkage from October 2016 to May 2017 would have happened due to, let's say, irrigation or other types of demands of water, right? So this is another application of spatial data, or data where we can find information which is delineated by space, right, which is, let's say, spatially delineated. We can find applications in natural resource development, right? So if we are supposed to manage water resources, probably we should look between post-monsoon and right before monsoon period and try and conserve water the most, because we see a lot of shrinkage during this period, right? Similarly, you have these urban development pictures. On the left, you have Golf Course Road in Gurugram in 2005 to 2021. You see the extent of development that has come about in 16 years period of time. Urban development, of course, it has urbanized, but it has not urbanized everywhere. If you look at the southwest region, that seems to have driven most of the urbanization, whereas the northeast region seems to remain, a lot of it seems to remain green, right? So this is urban planning. I mean, this is supposed to be local, local administration opening up land or allowing development or not, or it could even be driven by the geographical features of the area, right? There is a similar understanding which students can spend 30 seconds by looking at development in the Bandra Kurla area in Mumbai from 2001 to 2021, and see where and try and identify where component of urban development, in the sense, has it happened, where has it really happened, what are the areas it has not happened at, does it make any impact on on the water resource that we see there, what kind of impact would it make on the greenery, the green coverage of the area, and so on and so forth. Okay, so you can definitely try and identify these things on this picture on the right for Bandra Kurla, Mumbai. Okay, so welcome back. We will look at a couple more examples in this lecture. So the next example is the evolution of population density across Delhi. So what you see is from 2001 to 2021, the first thing you can see is we have more red blocks in the 2021 map for the NCR region, that is National Capital Region in Delhi, than we had in 2001. So we can say at the outset, the population density of Delhi NCR has clearly increased from 2001 to 2021. But then we can go one step further, like we have seen in previous examples, that we can identify what are the regions where this has really happened. So clearly, we have the region of Shahadra, which has seen a large increase in, or the dominant increase in population density among different regions of Delhi. We have also seen this in the Rohini region, and we also observe that we don't see much of an increase, or let's say not that much increase, in the southeast Delhi region of southeast Delhi region. The last sort of interesting example I want to talk about is the air pollution monitoring problem of Delhi. Of course, Delhi suffers from a air pollution crisis really, and different agencies, different administrative agencies have been trying to tackle this problem. How do they tackle this problem? Well, the first step is monitoring air pollution. Till we know how much problem, till we can measure the problem that we are facing, how are we supposed to, address it? So we have these air pollution monitoring stations, which are these green dots on the on your screen, which are spread across Delhi. Now, of course, these provide you the air pollution levels in Delhi at every, at very high temporal frequency, in the sense that you can go and measure air pollution levels every 30 minutes, or even with lower frequency, in these regions. So you may see that some regions are experiencing higher pollution levels than others. For example, East Delhi tends to have higher pollution levels than, let's say, some other regions, that is around, let's say, the airport region, the South Delhi region, and so on. But there is an environmental justice. There is a very interesting environmental justice problem arises here, is that, having these monitoring stations is costly, so we can't have them everywhere. But if the regions that we don't have these monitoring stations at, all these gaps, we don't really know what is the exact level of air pollution. Now the question arises, do the residents of New Delhi, where the density of air pollution monitoring stations is low, do they not deserve to know the air quality that they are breathing, right? Now this sort of sets off a problem that you can't have stations everywhere, but if you don't have them everywhere, you are actually sort of leaving the residents outside the opportunity of knowing the kind of air quality that they are breathing, right? To solve this problem, spatial statistics provides this tool called spatial prediction, in the sense that you can predict the level of air pollution at locations where you may not be directly observing air pollution levels during any given day or any given time, right? So it's a very interesting sort of, it opens up a very interesting dimension of spatial statistics, or something that it brings to table, which can resolve issues that are very critical, like environmental justice. Thank you.